I'm Ed Kohler, a principal engineer here at Extreme. Some of you I know from other events. I came from the Avaya acquisition. You may recall me from one of the tech field days that we did there. I'm going to talk about the fabric architecture here, and I'm also going to talk about some aspects of security. That happens to be one of my hobbies. We're going to talk about the subject of stealth networking and what it's all about and basically how it works. But before we do that, I'd like to talk about really a convergence of technologies that has been forced upon all of us, and that's IoT, BYOD, and cloud. If you look at these devices, they're wonderful. There's more computing power on this than there was that took us to the moon and back. But if you take away the cloud services supporting this, it quickly becomes just a really smart calculator. That's pretty much all it is. So cloud services kind of are inextricable to that. And also IoT is increasingly requiring cloud services as well, particularly in the residential space. So this is creating a bit of a perfect storm because it's bifurcating or sometimes even totally dissolving the traditional notion of what a security demarcation is all about. Okay, so that's basically the premise of what we're going to talk about here. This is a humorous slide. I like this slide. This was sent to me by a colleague of mine. There's some really good jokes in there. There's one particular highlight I would like to make, though, is I was on vacation with my wife and my daughter and her boyfriend. We were down in a city down south, and we were staying at an Airbnb. They had a smart home system there. They went down to town, and I was there catching up on some email, got through with my email, and being a security guy, I saw this on the wall, and I said, oh, I gotta look. Sure enough, it's on the open network. So people, it's an Airbnb, people coming in, coming out, and I was able to enumerate it as a Linux server, 2.6, and I mean, it was just, I told the guy, I said, you really should be segmenting these types of devices off of the common user network. So the problem is these devices are being put into the residences, into enterprises, and many times enterprises don't even know that these devices are existing or accessing their network. Now, to put a scope of reality on this, how many people know about and heard about Mirai? Okay, very serious event. Actually instituted the largest denial of service attack ever known. The best part about it is Netflix, Twitter, eBay, all of the companies that were affected were not attacked directly. It was an indirect attack vector. Basically what happened was Mirai was able to infiltrate into certain video surveillance cameras, home gateways, things of that nature, use known backdoors through credential compromise, and actually reside a botnet into that environment. From there was a coordinated DDoS attack that was launched against Dyn, which is a cloud service provider for DNS services. And you take away DNS, what happens to the internet, guys? We all know it breaks. So a total indirect attack. Okay, this is something that the nexus of IoT, BYOD, and cloud is making possible now. And if we don't think the attackers aren't leveraging it, we're foolish. They are, and they're leveraging it on a daily basis. We also think that there is a new and improved Mirai out there. Like all malware, once it gets out into the wild, sooner or later, nation states, different organizations, criminal organizations, things of that nature get a hold of the code. It's being weaponized. There are 11 new exploits, bringing the total to 27. New propagation and obfuscation methods of hiding, credentials for brute force, an improvement in that, and then also an extension of the target list. Scarily, much of this is infrastructure systems, smart digital signage, things of that nature. So it's something to watch. It's also not the only worm out there. It's not the only botnet out there. There are many, and as you can see from a quote from Palo Alto, Unit 42, that this is becoming more and more common to see these IoT Linux botnets. Now, the real solution, obviously, is to segment the network. And this is a comment directly from Rob Joyce, who no longer with the NSA Tailored Access Operations, but back then when he made these statements. And right there, you can see the red check mark that segmenting networks and data is obviously a smart thing from a security perspective. And we all know that. How come people don't do it? Okay. Well, the reason why is because it's complex. If you look at the traditional approaches, you're stuck with VLANs, with access control lists. I've seen some accounts where I've gone in and they've had 5,000 access control lists. And you sit down and you start to try to enumerate those control lists. And they don't even know what half of them are because they were created by people that aren't even there anymore. But no one wants to remove them because they were there for a purpose. So this becomes something that becomes complex. The other point is that with complex access control lists, you are the human, you're the coordinating, you're the one that is trying to protect the environment by these lists, which means that inevitably, you're going to fail. You're going to create a pinhole, and you're going to have some sort of vulnerability, and that has been shown time and time again. Humans just aren't very good at managing very large lists of numeric and profile type data. Distributed firewalls is another option. Many people will back up to this because it's quote unquote the easiest, but it is also the most expensive, particularly if you're trying to do this for internal segmentation needs. And then there are the overlay techniques, MPLS, IPVPN, VRF Lite. Anyone who's ever dealt with MPLS realizes it is not an easy technology to work with. You really have to know what you're doing, and it is fairly difficult to manage from an OpEx perspective. And the tunnel overlays, the complexities, the fact that we still have an open IP network underneath, and also a limited scale, particularly if you're dealing with large numbers of IoT type components and service devices. So with that, what we're going to do is talk about and introduce shortest path bridging, which is a standard with the IEEE. The standard is 802.1AQ. It's an evolution of prior standards, 802.1AH, which is MAC and MAC encapsulation, provider-based bridging, and the incorporation of ISIS through RFC 6329 and the IETF. That combines to make IEEE 802.1AQ, shortest path bridging, and that has been since grandfathered into 802.1Q standards as of 2014. Now, the origins are in the service provider space, as I said, so that brings sonnet-like stability to Ethernet, as well as carrier-grade separation of services, which I believe you guys have experienced.
So a question for you on that. When you say MPLS-like functionality without MPLS-like complexity, which aspects of MPLS are we talking about? VPN, L3 VPN, which?
All of them. We'll talk about
what
it.
Are the, what specific, because, shortest path bridging, as I understand, is purely a layer 2 technology.
It's a layer 2 technology based on Ethernet, and I have some slides that'll go through this.
Gotcha.
Basically what it is service instantiations over that layer 2 forwarding domain, and I'll talk about that.
Right. Okay.
So this technology is very good in, as you pointed out, MPLS functionality without the MPLS-like complexity. It is simple, it is fast, it is flexible. It lends itself extremely well to automation. This is one of the things that you'll find. Now, let's do a deep dive into the protocol. What I want to do is just go over a few basic tenets of it before we actually start to talk about some use case parameters here. There are really three main components. As I said earlier, the standard of 802.1AH, MAC and MAC encapsulation, that provides the data plane for us. This does not use IP, the Internet Protocol, in order to establish topology, or in order to establish any forwarding or delivery of data in the fabric. That's an important aspect because as attackers, as red teamers, one of the things that we look for is to enumerate a network, to identify the network, to enumerate the systems, match those to vulnerabilities, identify those, match those to exploits, and then try the exploits on the system. But in order to see that, you have to be able to discover the system, and you have to be able to touch the system. If you can't discover it and you can't get to it, then it becomes very difficult to do the vulnerability assessment or the exploitation. And that's one of the big things here. Service identifiers are unique type entities. They work inside the context of the tunnel, and they match to different clients. So tenant A, tenant B, tenant C, or application A, application B. So maybe digital signage, video surveillance, building management systems, or it could be police department, governor's office, attorney general. Multi-tenancy is multi-tenancy. It could either be human-based or application service profile-based. These ISIDs are very powerful. They can be layer 2 entities, or they could be layer 3 entities. And I'll go through the details of the difference as we move forward. But when I say layer 3 entities, we are talking a true IPVPN environment equivalent to IPVPN, which is RFC 4364. Now, the last piece is the ISIS control plane. The important thing I'd like to emphasize is we don't invoke ISIS as a routing protocol. If we did that, then we'd just be doing the hop-by-hop label swapping and forwarding like ISIS has already done. What this does is it programs the Ethernet forwarding database environments. It's a strict control plane. It moves no user data whatsoever. All user data moves through the scope of the ISIDs in the 802.1 AH encapsulation, which means the network is dark.
So similar to protocols like Trill, you're taking advantage of the fact that ISIS runs its control plane at layer 2 and not layer 3.
Correct.
And you're using that for your control plane to build.
And extensive type length values to describe the surface characteristics.
Sure, got it.
Okay. Okay, so with that, we come to a technology that basically has an Ethernet forwarding plane that has very fast fallback characteristics, under 100 milliseconds, is able to support multicast with unprecedented scale without the use of any routing protocol support, including PIM, and also probably one of the most secure networking technologies on the face of the planet because the segmentation is absolute. Oh, last piece. There is no spanning tree protocol. There is no flooding within the fabric, and there's no learning within the fabric. All learning is based on a divided edge phenomenon that happens at the service edge of the network infrastructure, which makes things like ARP poisoning, MAC spoofing, things of that nature very, 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 very difficult. Okay. Now, this is a technical look at what happens at the user-to-network interface edge. One of the things I want to point out is at the point of the user-to-network interface, there's an encapsulation into the 802.1 AH superframe. There is no visibility from the UNI edge into the service core as a result of that. There is no way to inject data into the service core as a result of that. There is no way to spoof AH-type framing at the service core to get past and trick the switch. It will all get dropped at ingress. That happens often as well with attempts at MAC spoofing and things of that nature, as we will drop it at the ingress. It just simply does not get forwarded. The important point, though, is we have an orthogonal service and addressing scheme. The actual tunnel identifiers provide the MAC and MAC encapsulation, and then the service identifiers are the ISIDs, which basically work as context of services, different multi-tenants within that AH tunnel. Okay, so think of them as individual VPNs, whether they be layer 2 or layer 3. Okay, now the point of this is that because these things are separated and they're orthogonal, I can have a failure in any network and these ISIDs will reroute according to the database requirements. So when the fabric comes up, it establishes all known paths. And once those paths are known, the ISIDs basically fall on those according to the shortest path bridging behavior, the best optimal path, hence the standard. But what happens is if there's a failure, there is no need to reconverge the network infrastructure. The switches automatically have the alternate paths loaded into the database. ISIS still needs to converge. We still have to recognize a node goes down or a trunk has gone down, but the switches don't have to wait in order to forward on the alternate paths, which means that we can provide full uptime for services like video surveillance, things of that nature. Okay. Now, to get a better scope on this, this is what happens end-to-end across the infrastructure. The actual client MAC frame is ingested, encompassed into a basic superframe. We use the destination and source addresses of the BMAC frames within the core to move data across the infrastructure. This is how we solve the issue of doing path behaviors at Ethernet without requiring IP. IP now becomes totally virtualized as a service phenomenon around the edge of the network. Now what happens is the database coordinates the presence of a subnet, for instance, to a particular switch, which is exactly what you're seeing here. ISIS is a great protocol. One of the unique parts about the architecture that we selected is the fact that it's a horizontal service plane. If you look at the legacy model, which we all know works, we have layered dependencies. And another thing, for those of us that have played with these protocols, they're kind of ships in the night. They're not aware of one another. We have to string the service chains together. And there's top-down dependencies in this, so that if failures happen at a lower level or a misconfiguration happens at a lower level, the rest of the stack is kind of like a house of cards. It's one of the reasons why with a big MPLS network or a big VRF network, you don't go in the middle of the day and light up a new VRF and try to implement PIM on it. Because if you try that, you know you're not going home that night. You may as well call your wife now and say, you know, I'm not going to be home tonight because the network's going to be down. You just wouldn't do that. You wait till the wee hours and then you come in and you basically make those service changes to the core because it's intrusive. One of the benefits that particularly our healthcare customers have found is that because of these mutually independent horizontal service categories, they can go into the fabric, they can create a new VRF, a new IPVPN in the middle of the day, light up multicast in the middle of the day, and they're assured that the hospital and the rest of the services will still be running. As a matter of fact, they can go into an existing IPVPN environment, add a new VRF, add multicast to it in the middle of the day, and they won't affect the operation of the rest of that IPVPN environment. That's something. And to a hospital, that becomes a very big thing from an OpEx perspective. Another vertical that has realized this capability is manufacturing. Because manufacturing, it's very costly to get IT involved in rearranging and moving production floors and different flows. Now with this technology, it allows them, pretty much the blue-collar guys, to do all of the flow remodeling on the fly. And they just replicate the IP addresses again and again and again because they're assured that the flows will never see each other across the fabric.
So I've got a question for you on
Yes.
multicast, because I spent a fair amount of time in IPTV and broadcast video multicast. What kind of scale are you seeing with that? If you're going to simplify multicast routing by using a layer 2 overlay, I'm assuming that's one of the use cases.
We use ISIDs to deliver.
What kind of scale do you see for that?
Well, I'm going to give you a couple case point examples. We did some testing with the TSA to be used in some of the major airports. We went into Fresno, California, and Schneider Electric's scaling lab. We were able to scale out to 14,400 high definition feeds.
Okay.
And still have 100 milliseconds failover.
Now, how was that subnetted exactly? If that's
they were just standard /24s.
okay,
Yeah,
gotcha.
it's pretty much the way the airport was laid out. Now, I do want to share with you that we have a major casino can I use the name? MGM Grand? Okay, yeah. Okay, MGM Grand, can I use it? Okay, all right. It's a small casino. They're basically running 32,800 cameras, 24/7. All multicast based.
Okay.
You'd never get a PIM environment to scale to that.
Gotcha.
Okay. And by the way, that's my contribution to the standard. That actually is one of my sweet spots.
Are you saying this is because you're obviously subnetting this out, so you aren't doing this all in the same layer 2 domain? Is that a replacement for PIM in what you're doing?
Oh, absolutely.
There's an assist for multicast here?
Absolutely.
That displaces
Absolutely.
PIM? Okay.
So remember, ISIDs are always directionally graph trees, okay? At the lowest level, everything that happens inside the Ethernet fabric is directionally graph based. Now, directional graph trees are basically the way multicast is delivered. So ISIDs are the perfect element. Plus, they're not based on IP.
So this pairs well with IGMP for
Correct.
for a service, for an IPTV service.
Absolutely.
IGMP.
If you took you're an IP television guy, if you took an existing head end, set-top boxes,
Right.
so forth, so on, took the PIM out and put this in place, the systems wouldn't know the difference.
Okay. Interesting.
Okay, so story's correct, right? You can see that there is a vast flattening of the stack. The removal of service dependencies. I don't have to build layer 2 services before I overlay layer 3. And I don't have to build an IP underlay before I can start to build IPVPNs. All of that is based on the Ethernet fabric as a programmatic instantiation, okay? So, how do we enable stealth networking design? Well, one of the things that happen is in traditional networking, when you come into a network, you have a lot of touch points. And you have to go in and basically work across this infrastructure and try to lock it down. In the SPB service contract, we can basically get a very high granularity, one-to-one service construct in a fairly granular fashion. You can see we're using PSI, video, patient records, and imaging here. Now, in the case point, when you start looking at a traditional network, if a person can get into the network and finds an open network, which the NSA said happens about 60% of the time, you basically can move east-west. You can enumerate the network infrastructure. You can create pivot points. You can create exfiltration channels. And then sooner or later, I start to pull data. And advanced persistent threats do this very quietly. Matter of fact, most advanced persistent threats are in a customer's network on the average of about 200 days before they start anything active. So they make sure they have as much knowledge of the network infrastructure as possible and as much command and control points of pivots as possible, because when they start to move data, it's not just a big long FTP train. They ride it through ICMP, they ride it through DNS covert channels, they ride it through SIP, all sorts of different protocols. Skype actually was used quite actively for a while for exfiltration. I think that's stopped though. But anyways, to make a long story short, there's many ways that bad people can pull data out of the infrastructure. The main point with SBB is even if someone did, for instance, compromise a video surveillance camera, they can only stay in the segment that they're in, and that's basically being demonstrated here. Yes, you can compromise perhaps maybe a Mirai botnet, or someone gets in with a USB or direct access to the systems, which you've got other problems if that's happening. But the point is that if it were to happen, the compromise would be contained. And the visibility would be contained and minimized so that it would be really quite impossible for the attacker to enumerate anything outside of the segment he's in, okay? Or she. There are women hackers. Okay, the next thing is the type of stealth segments. We have the ability to take ISIDs and associate them with VRFs. When we do that, the ISID becomes the peering entity. So in a normal VRF environment, you peer with BGP, okay, or IPVPN Lite or something of that nature. Here we're peering with the ISIDs. The ISID is not based on IP. It's an Ethernet circuit. Therefore, it's a dark network. There is no routing protocol between the VRFs to enable that, but the IP forwarding domain runs between the two VRFs and creates basically a gigantic VRF out of the environment. Now, that is great because this allows segmented routing tables, largely isolated from one another, unless I match them and marry them through security demarcations, and we'll talk about that a little later. But it also gives multiple subnet support as well. There is also a very stealth type technology which are called layer 2 service segments. They are not based on any type of VRF. They're a termination of a layer 2 service entity to the ISID itself. And that can either happen with a physical port, a VLAN, or a tree-based type of phenomenon, which we call E-tree. We can also do switch services and transparent type services as well. So if you need to pipe over, let's say another agency came to you and said, hey, I need to get from one building to the other, can you get me across your core? You can do that with the transparent UNI. You can just give them one point to another. They can write over your core, and there's no connection to your network infrastructure. It's absolute separation, okay? So some very good services that are combined here at the layer 2. The important thing is that this becomes very good for SCADA, traffic control services, things of that nature that are often used in the cities and local metros. And obviously with SCADA, we get involved with that, manufacturing and things of that nature. But also SCADA is often used in the transit authorities for railway controls and things of that nature. Okay. Reducing the touch points. As I talked about earlier, all of the previous methods of doing microsegmentation require a lot of heavy lifting. Even the overlay stuff, you have to build a lot before you can even start implementing overlays. But certainly MPLS, other technologies, access control lists, they're all high touch. They require a lot of interaction with the service core. Whereas Fabric Connect is really edge configuration only. The only thing we do is provision the service edge, and the core is programmed by the database instantiations that I talked about earlier. So ISIS takes care of all of that for us. When we go into the service edge and we set up an IPVPN, for instance, the first thing the switch does after I hit the return button and say provision is it goes out and it sends an ISIS triggered update to every other switch in the fabric. Every other switch in the fabric then updates its database to link and correspond to the environment. And again, this all happens from a directional graph perspective. Okay, so there's no possibility of any routing loops. Okay, that's how we eliminate spanning tree. So when you start to look at this, we have a number of things here. We've got a 24-bit service identifier. If you do the math on that, it's the exponential value of 4096. We take away a 1 because you can't have an all-zero circuit. So that gives us 16,777,215 ISIDs. in a flat service space, which is a pretty big service space. The other point to this, though, is that all of these circuits can be used for either layer 2, layer 3, or multicast. We have one large EMEA hospital in Northern Europe that has 1,600 layer 2 and layer 3 segments throughout its hospital network infrastructure. Hospitals tend to be very, very highly segmented for obvious reasons. Now, the other point is the segments are easy to set up. I don't have any command line sequences here, but really it's a one-line command to set up an L2 VSN. It's about 7 lines of code to set up a layer 3 VSN. And keep in mind that if we were going to set up an IPVPN and MPLS, you'd probably be out to 120 lines of code to set up a service instantiation. So a big consolidation of command line activity in concert with the protocol optimization that ISIS and the programmatic database gives. So it's a great combination that really translates into stronger security profiles, easier to audit, and better OpEx profile. Very few technologies offer that, all three. So we can combine and work with partners in the industry. As was spoken about earlier, we realize that we don't do things all alone. Extreme is a networking company, and we have a fairly broad portfolio. But we don't make intrusion threat detection systems. We don't make firewalls. We do, however, make NACs. But the point is that these exterior technologies work in concert with the fabric, but note how they're always on the service edge. So that now, if I have a physician in an imaging service, there is no type of a way that I can allow an unauthorized type of access. And a great example is a physician coming into a hospital, and they often have an iPad, and they typically don't want to deal with anything in IT. They just want to come in, they want to pick their patient's records, and they want to look at the MRIs. That's it. We can allow that, okay? But we don't need to give the physician access to the MRIs directly. Nor do they need access directly to the picture archival system. I think we'd all say that would be a bad security move, right? Because doctors are just people, just like the rest of us. So we have to keep a separation and the ability to monitor the activities between the segments. So this basically creates a policing function. The ability to actually isolate, look at things going inside and out of the segment, north and south, becomes very powerful because it basically alerts you to anomalies in your actual security profile. Changes are very seldom good in IoT. Okay, I'm going to repeat that. Changes are very seldom good in IoT. Okay, if you see an IoT device doing something different that it's never done before, that's not a good sign almost 100% of the time. So that becomes very, very key. The other point, though, is this can watch for anomalies with humans. Humans, once they change their tactics or their hat, if you will, from white to black, they will inevitably change their behaviors. They're going to start to pull data from servers they've never pulled before. They're going to start accessing databases they've never, and you'll see those changes in profiles, and that should be investigated. Now, obviously, this isn't an absolute answer to that because there are application logs, database entries, things of that nature that you should be monitoring as well, okay? Because if someone's accessing a direct database through SQL injection queries, you should be investigating what the hell's going on because there's no way they should be accessing a database in that fashion.
So from an IoT standpoint and security and all that, are you doing anything like geolocating on that stuff, geofencing?
Yeah.
Okay.
Yeah. So when you look at it,
more healthcare.
When our network access control authenticates the device, and then authenticates one thing, but then authorization is the final thing, and that's where geolocation comes in, okay?
So,
and that's actually where the ISID kind of matches into the policy.
Right.
Okay.
I'm just thinking more of like a pump or a monitor that only does PSK.
Yeah.
So it's not necessarily all the way back to the NAC.
Right. In that instance,
how are you handling that?
In those instances, those types of devices, we would usually invoke something of this nature. This is Defender for IoT. Many IoT devices do not have the CPU resources to think themselves out of a paper bag. So,
Yeah, I mean, they can only do basic security.
So this will present a certificate on behalf of the IoT device. It will authenticate on behalf of the IoT device as a bonded asset. Yeah, and then basically we can manage it, and there are firewall functions in there with whitelist policies and things of that nature. That can be used either in conjunction with Fabric Connect, or it can be used in a network that has not yet converted over, and they just want to protect IoT devices, because that will actually work in an IPsec mode as well. Okay, this is an example of what I call a bifurcated policy, or data corralling. This is also something that's recommended by the NSA. Now, we did this in concert with Ascension Health, which is a very large healthcare network. They actually traverse multiple states in this country. I think it's one of the largest healthcare networks in the nation. We did this with them because we created the IoT Defender very much in concert with them, because they came to us and they gave us the challenges that they work against every day in healthcare. Many of these devices are very, very vulnerable. They're running Windows 98. XP, I mean, it's just crazy stuff. You can't even upgrade that stuff anymore. So the point is they needed to have a protection mechanism. And so there's two ways we can do that. We can either use the IoT Defender, or we can use extreme policy. And in this example, you see that we have a bifurcated policy where we have a layer 3 VSN that contains the multiple subnet environment. Now, that by itself will bound and constrain all traffic within this environment to that L3 VSN. You also see that we have policy rules that we've established, where we have the IoT server port dialog, and that's a fake port. It's not the real port number. But anyways, we take that port number, we direct that and allow it only to the IoT server. Therefore, there's no way that the IoT control traffic can traverse outside of the actual L3 VSN environment. It's constrained to that environment by policy. But you can also see that we allow port 80. That's also not the port number. The ports have been changed to protect the innocent. And you can see that now the physician can come into the hospital, gain access to the firewall, to the actual IoT server in the picture archival, pull the images so that they can get the patient images, but there's no way to directly access the systems. Okay?
So can you deploy this in monitor mode? Is there discovery, or do you have to come with this data?
That's actually what we recommend. When people put extreme control in the first time, we recommend we put it in monitor mode. Okay. What it does is it will actually do a complete inventory assessment of everything that touches your network. It doesn't do anything from a policy perspective, but what happens is you get a huge enumerated list of what's on your network, and some people are stunned. Stunned.